In this video, we're going to derive the push-forward or Jacobian-vector product rule on neural ODEs, or you could also call it final time integration of ordinary differential equations. And if we frame that as a function, I want to give that the name q that depends on a parameter vector theta as well as an initial condition u0 and a final time t. It shall be given kind of implicitly by the solution to an ordinary differential equation. So we can say solve and then the ODE du by dt, and with a vector u is given as the right hand side on vector u and parameter theta. And this shall be solved for the solution function u of t, so a vector valued function that depends on the time, and then we should evaluate this function at t equals capital T with initial condition u at t equals 0 being given by u0. And I want to call this result u evaluated at capital T. And that's our problem description, which is abstracting away how you would actually solve this. Typical approaches are, for instance, explicit integrators, for instance, with an adaptive time stepping. So you could use a Runge-Kutta 4-5 scheme, and really common values for this Runge-Kutta 4-5 scheme might be those 2 Dorman and Prince. Let's add some dimensionalities to the quantities here. So we have our theta parameter vector, which we want to say is p-dimensional vector. So this is the parameter vector. Then we have u0, which is an n-dimensional vector, and this shall be our initial condition. Then we have t, which is a real valued number, positive number, and this is the final time. It defines our time span of the ODE integration. That could, for instance, be 1 or something like 1 time unit, so 1 second, for instance. And then we have u at capital T. This is the output of our function. It will be another n-dimensional vector, and this is the final state. And it is crucial that this is not a function. This is one vector. Despite us describing the problem with a differential equation, which is in terms of an unknown function, here we are only interested in the final state. And this is also an analogy to other neural networks. So neural ODEs are just some continuous analogy to resonance, since neural ODEs are inspired by a resonance looking like an Euler discretization to a differential equation. So in that sense, when you have neural networks, you're also not really interested at the values that are at the hidden layers, but rather only at the output. You could also look into the push-forward rule or the Jacobian-vector product rule for full ODE integration, where your goal is to get the full solution function or to have it evaluated at certain intermediate points, but here it's only for the final point. I will also have a video on the full ODE integration. It is a little bit more tricky, but it follows similar steps. Let us write this down once again, that here we are only interested in the final state. So let's say we are only interested in the final state, so the solution function evaluated at the final time, and we are not interested in the full trajectory. Okay, so far so good. That is our primal problem, to integrate this neural ODE or just to have a general ODE and integrate it all the way to our final point. Now for this video, we are interested in propagating tangent information. So this means the task of what we want to derive is a rule to forward propagate tangent information on the input, and the input to our function is parameter vector theta, for which we now have a tangent version. I want to integrate with a dot on top, which will be another p-dimensional vector. We also have tangent initial conditions, so this will be an n-dimensional vector, as well as some tangent information on the length of our integration interval, which will be a real valued number. And we want to forward propagate this to the tangent value at the final state. So this is a vector and not a function again, but it is in its tangent form, an n-dimensional vector. And we want to do this in more general terms. So you could also have the case where you only have tangents on the parameter, but have the initial condition and the integration time fixed, or you have 2 out of the 3. So this is all possible. Of course, this will then simplify the actual rule, but here we want to derive it for tangents on all of the 3 inputs. And then an important remark here. Similar to the other implicit rules we derived so far, we want to do that without unrolling. So without unrolling the solver and applying forward mode automatic differentiation to its operations. In the literature, you also sometimes find the word piggybacking for this, because what we are doing, or actually what we don't want to do, but in that case, what we would be doing is in that we say that if we, for instance, use our Runge-Kutta 4-5 scheme, this in the end will boil down to some linear algebra operations. That could be in terms of matrix vector products, or even more granular in terms of scalar additions, scalar multiplications, and so on. If we break down our computational graph into these really small operations, we could just use an automatic differentiation engine and then apply it to this larger computational graph. This is a valid alternative if we can apply it, but oftentimes when we solve these implicit problems, like ordinary differential equations, but we also saw that for linear systems of equations, one might want to employ a highly specialized routine that is called from a different language or from a different library, which makes better usage of your available hardware. And oftentimes these particular routines are not written in a differentiable way, so it's not that easy to differentiate through them, and we have to provide custom differentiation rules, here in that case for forward mode, AD, and then there is no alternative to doing what we are presenting here. Sometimes it works, but here we want to derive it in this general implicit sense. The general push-forward or Jacobian-vector product rule would read the following. So what it kind of does is that it gets the tangent on the output by taking all of the inputs, so we have 3 inputs, and deriving the Jacobian of the function, so of our wrapper integrator, with respect to that input, and then contracting over the tangent. So in other words, it would be the derivative of q was the integrator function, with respect to the parameter vector theta, and then multiplying it with the tangent, plus the derivative of q with respect to the initial condition, and then multiplying it with q0 tangent, plus the derivative of q with respect to the final time and multiplying it with the tangent on it. And these 3 quantities are tricky ones because q is our wrapper integrator, so it's the rather general abstraction. How do we obtain that Jacobian? And essentially what we will be doing in this video is deriving an alternative way of expressing this Jacobian vector product. And in order to do that, I want to give these 3 individual names. So let me call this one here the contribution to our final point from the parameter vector theta. So let me add the underscore here. And at certain points, I will also drop the dependency on capital T here in order to have it less cluttered. This will be the contribution to the tangent from the initial condition. And this will be the contribution to the tangent from the final time. And I want to proceed in the way that we will derive each of the contributions individually, and then ultimately we can add them up. So let me introduce 1 and 2 and 3 here, and then we will first start with the contribution from the parameter. So let's have this point 1. This is the tangent contribution from parameter vector theta underscore. And in order to find this, let us write down the general solution to an ordinary differential equation. So this is the general solution to an ODE, especially if we're only interested in the final time integration, and that you say that u at time capital T is u0 plus the integral from 0 to capital T over f of u at t, and then the theta vector integrated dt. So this is kind of an alternative way of writing down our ODE problem to already find some kind of an implicit expression for the solution at point t. And now we want to take the total derivative of this expression with respect to the parameter vector theta. So let's take the total derivative with respect to the parameter vector theta. So what we will get, the derivative of u at capital T with respect to theta is the derivative of the initial condition with respect to theta, plus, and then our derivative operator propagates over the integral because both are linear operators and the limits do not depend on theta here. And then we have the derivative of f with respect to theta. And then we see that our right-hand side has both an explicit dependency and an implicit dependency. So it is explicitly dependent on theta, but we also have an implicit dependency of u on theta. So we have to resolve that chain. So we will get the derivative of f with respect to u, then times u with respect to theta, plus, and then f with respect to theta. And this integrated over t. Okay, now we found an expression for the Jacobian of the final time with respect to theta. So essentially, this is what we also have here. So if we alias the function with its output, So we see that the Jacobian of q with respect to theta is essentially the same as the Jacobian of u at t with respect to theta. So we can also write this down, that this is equivalent to u at capital T with respect to theta. And then we see we essentially found an expression for this Jacobian. This will be a matrix now, and essentially if we see an analogy to the general solution to an ODE, it will be an ODE for this matrix. But for our tangent propagation, we are not really interested in a Jacobian. And more generally, whenever you do automatic differentiation, let it be forward or reverse mode, you're not interested in the full Jacobian, but just its effect on a vector, and in that case, in our forward mode, the Jacobian-vector product. So let us multiply this equation with theta dot from the right. So we will multiply with theta dot from the right. Okay, let's do that. And then we get on the left-hand side of the equation that we have the derivative of the final value with respect to theta multiplied with theta dot is equal to the derivative of the initial condition with respect to theta multiplied with theta dot plus the integral from 0 to capital T of the Jacobian of the right-hand side to the ODE with respect to the input u multiplied with u with respect to theta multiplied with theta dot plus the derivative of f with respect to theta multiplied with theta dot and then integrated dt. Okay, let's take a look at that. And this is the essential output that we want to find. So in other words, this is the tangent u at t contribution from theta. So that's a little mouthful, but essentially this is essentially what we have here as component 1. And then let's go on. Here we see the derivative of the initial condition with respect to theta. And here we assume that the initial condition does not depend on the parameter vector theta. So the theta vector only acts on the right-hand side of our ordinary differential equation. And as such, that will be the zero matrix. And if we then multiply the zero matrix with the tangent, this will just be the zero vector. Okay, let's go into the integral. And here we basically see that we have the Jacobian of u with respect to theta evaluated at theta dot. And now we have to make a little bit of a self-fulfilling prophecy in that we ultimately want to derive an additional ordinary differential equation which we want to solve in order to propagate the tangents. So we can kind of see that as u tangent contribution from theta, but throughout the integration interval. So during the time from 0 to capital T. So in other words, this will be u dot at t. So this is not at capital T, but at t and contribution from theta. And if we then write that down again, we see that this is essentially the general solution to an ODE again, which we can extract into the other form of writing down an ODE. So let us do that and see that we have u tangent at capital T contribution theta is equal to, well, 0. Let's keep it for generality. So a zero vector plus the integral from 0 to t over the Jacobian of f with respect to u multiplied with the tangent on u at t contribution from theta plus df by d theta times theta dot integrated over t. And this is essentially the general solution to another ODE problem. So let's write this down. This is the general solution to the following ODE. And this ODE looks as that we have the derivative of u contribution from theta, u dot contribution from theta by dt is equal to the Jacobian f with respect to u multiplied with u contribution from theta plus the derivative of f with respect to theta, so another Jacobian multiplied with the theta dot, and then as an initial condition we have the zero vector. So u dot theta at time equals 0 is the zero vector. Let us try to write that down in the same format as we had it for the primal problem, so that we said that the solution is given verbally here as this implicit problem through the ODE integration. So we can say that u contribution from theta at point t tangent is given as the solution to the ODE du theta dot with respect to t is the Jacobian of the right-hand side with respect to u multiplied with u theta dot plus the Jacobian of the right-hand side with respect to theta multiplied with theta dot. And this shall be solved for u theta at time t dot. So here I put the brackets after the index, but I think you get what I mean. And evaluate at t equals capital T with initial condition. And here we said that the initial condition has to be u dot theta at t equals 0 is the 0 vector. And here we also see again that this is another vector valued ODE problem in contrast to what we derived for the Jacobian, which obviously was a matrix valued ODE problem, but due to us right multiplying with the prescripted tangent, we actually boiled that down into a vector valued ODE problem. And I want to analyze that a bit further. So the theta dot is something that is given. So that's just a fixed value that we are provided with, that we shall be propagating. But how do we obtain this df by du and df by d theta? But if we look closely at it, we see that these are just more Jacobian vector products. So let me add some more space here. And then we can add that remark that this one as well as this one is a Jacobian vector product. So Jacobian vector product, and we hope, or even if it was not the case, we could also adapt for this, but if f is given explicitly, so as a function, so composed of, let's say, some multiplications, additions, some exponentials, whatever, we could use a forward mode automatic differentiation engine in order to evaluate that Jacobian vector product. Or in some cases, like if you want to simulate PDEs, writing down the Jacobian is often possible to do analytically since it has a sparse structure, and then we have access to this function, or we can rebuild it at the corresponding u points. So we could either do this by autodiff or by knowing the Jacobian, And let me also remark a little bit on what kind of type of ODE problem this is. If we go all the way to the beginning to our primal problem, we wrote that down in a general notation. So this can be a nonlinear ODE problem, for instance, arising as the method of line discretization from a nonlinear partial differential equation, or it is just a more general nonlinear ODE problem like the Lorentz attractor or some other problems. But the interesting observation is that this, sometimes also called tangent linear problem, is an, as the name suggests, a linear problem. So this is a linear ODE. So the tangent linear problem for the parameter tangent propagation, because we are still under point 1, is a linear ODE. And we can additionally observe that it is a forced linear problem. So we have a term here, this df by d theta times theta dot, which does not depend on the unknown in that ODE, which would be u theta dot. So in that case, it is forced. So it's also forced. It is forced, or one could also say it is inhomogeneous in the ODE. So it is inhomogeneous in the ODE. And it has a 0 initial condition. So a 0 IC, which means it is homogeneous in the initial condition. Okay, cool. So this is an auxiliary problem that we would have to solve in order to find this u theta evaluated at capital T dot, so the contribution to the tangent at the final time from the propagation of the parameter vector. So it's a mouthful, but at least essentially if you solve this problem with your Runge-Kutta integrator, then you obtain contribution 1. Okay, let's go on with contribution 2. This one will be now a bit quicker because we already know how we have to proceed. So point 2 is the tangent propagation from the initial condition, and this is u theta. If we now go into the analogy of neural ODEs and multi-layer perceptrons, that would mean if you want to propagate tangents from your input to your neural network, whereas in point 1 we propagated tangents from the parameter space of our neural network, because like classical MLP problems, they usually live in these two spaces, both a parameter space as well as a state or input space. And for this very first problem, we propagated from the parameter space, and now we will propagate from the state space. Okay, let us start again with the general solution. So we will again take the general solution, and that one was u at capital T is u0 plus the integral from 0 to capital T over our right-hand side, which was f of u of t of theta, and then integrated dt. Then we will take the total derivative of that expression with respect to the initial condition. This will give us the derivative of u evaluated at capital T with respect to the initial condition is equal to the derivative of the initial condition with respect to the initial condition plus, and then our derivative operator again propagates over the integral, so we will get the integral from 0 to capital T of, again, the Jacobian of f with respect to u multiplied with u with respect to theta 0. And we don't get any additional contribution or addition here of f with respect to theta because theta does not depend on u0. And then let's integrate dt. And again, here we would have an expression for the Jacobian. So how does the output of our integration correspond to the input of our integration? We are not interested in the Jacobian as before, but rather in the Jacobian-vector product. And let me highlight this once again. So if we go all the way up here, we are interested in point 2, so the multiplication with the tangent on the input. So let's multiply this from the right. So let's multiply with u0 dot from the right, and then we get the derivative of u at capital T with respect to the initial condition multiplied with the tangent on the initial condition is equal to the derivative of the initial condition with respect to the initial condition multiplied with the tangent on the initial condition plus the integral from 0 to t of the Jacobian of the right-hand side with respect to the input u multiplied with du by du0 multiplied with the tangent on u0 and then integrated dt. Okay, let's analyze that. Here again, we can extract our tangent contribution. So this will be u at capital T contribution from u0 tangent. And then we have here the derivative of something with respect to itself. So initial condition with respect to initial condition just gives us the identity matrix. And if we multiply the identity matrix with a vector, you will get that very vector. So it is the tangent on the initial condition plus, and then we have the integral from 0 to t. And here we will see an time-dependent contribution from u0, because again, as like with the contribution from the theta vector, we will have to solve an auxiliary ODE problem. So we have the Jacobian of f with respect to u multiplied with u dot contribution from u0, and let me add that underscore, and I think it is even more precise if I add this dependency on t here. So it's a little bit complicated here, but the interesting observation is it kind of gives us something similar to what we saw with the parameter vector. So again, don't miss the dt here. And if we write that down in the same format as we had it before with this implicit solve, we see that the contribution to our tangent on the output at capital T from the initial condition u0 is also given by the solution to the ODE problem. So solve d u dot from u0 dt by the Jacobian of f with respect to u multiplied with u dot contribution from u0 or u dot contribution from u0 on t. So this is still the function, and evaluate at t equals capital T with the initial condition being set to u contribution from u0 evaluated at t equals 0 is u0 dot. Obviously, this kind of makes sense to me. Hope it does to you as well. So we solve an auxiliary ODE problem for which the initial condition is the tangent on the initial condition. And again, we can make some discussion on that problem. So essentially what we see here is another Jacobian vector product, same strategy as before. We can either evaluate that by autodiff, so by autodiff, or by knowing the Jacobian, And in contrast to the problem we had for the theta vector, which I think it's an interesting contrast here, is that we see now our problem, I mean, it is still linear. So let me write this down. This is still linear. It's again a tangent linear propagation, so it will be linear. But in contrast to what we had before, it is now homogeneous in the ODE, but it is inhomogeneous in the initial condition. So in the initial condition. That's quite cool. Okay, that's contribution from point 2. The last one will be a quick one. So this is the tangent contribution from the final time. So in other words, if we have some tangent information on the final time, it's a little bit abstract on what that could be, but if you have an optimization problem for which you want to find the optimal length of the integration interval, if that makes any sense, then this would be something where you would propagate gradient information over that, so as part of an optimization problem. Okay, how does that work? Again, we will look at our general ODE solution. So again, general solution to the ODE, and I want to write it down once again. So it is u at capital T is u0 plus integration from 0 to capital T of our function, which depends on u, which depends on lowercase t, as well as theta, integrated over dt. Then we will take total derivative with respect to capital T. Then we have the derivative of u at the final time with respect to how long the integration time was is equal to the derivative of the initial condition with respect to t plus, and now we have to be careful, now the dependency on capital T for this integral is in its upper limit. So the inner part of the integral does not depend on that and only on the limit. And if we have this very case, we can simplify that, and this will just be the evaluation of the integrand at the final time. So it is f evaluated at u at capital T and theta. Okay, then similar to before, we multiply with t dot from the right. So it's a little bit of an overstatement to call that a Jacobian because we just derive with respect to a scalar, but still we are not interested in this, in quotation marks, Jacobian, but in the multiplication of that with the tangent. So then we will get the derivative of u at capital T with respect to capital T multiplied with the tangent on capital T. And then we have the derivative of u0 with respect to capital T multiplied with capital T dot, and then plus this expression, so u at capital T and theta multiplied with theta dot. Okay, then let's again look at that expression, and on the left we find again the quantity we are interested in. So this is u dot at capital T contribution from capital T, and here we see the derivative of the initial condition with respect to the final time. So how does the initial condition depend on the final time? So they do not depend on each other. So this one would be just 0 or the 0 vector, and then if we multiply t dot with that, so this will then just be the 0 vector plus, and this one stays as is. And as such, we see that in order to propagate the tangent information on the final time, we do not have to solve an auxiliary problem. So this is just an multiplication of the final solution, or the right-hand side evaluated at the final solution, with our concrete parameter vector multiplied with the tangent on the final time. Okay, let's summarize that. So we now have our three contributions down, so we can then write down a summary, and we will obtain all the components for our push forward. So the first component is the tangent contribution from theta at the capital point. So this will be a vector. And this one is integration of the ODE. So let's say integrate du theta dot with respect to t is equal to the Jacobian with respect to u multiplied with u theta dot, plus the Jacobian with respect to theta multiplied with theta dot, with the initial condition that u tangent theta contribution at t equals 0 is the 0 vector. This was the very first one we derived. Now we have the second contribution. This is the tangent contribution from the initial condition at the final time. And this will be the integration of du u0 with respect to t is equal to the Jacobian with respect to u, so the same Jacobian multiplied with u u0 with the initial condition this time being non-zero, so it will be the tangent on the initial condition. And let me also leave the remark here similar to what we also had in the primal, so that both problem 1 and problem 2, which is in that sense similar to the primal problem, so the primal problem was the original ODE, we do not need the full trajectory. So we're not interested in all the values of these tangent contributions over time, but only at the final point, because that also matches the primal problem for the neural ODE or the final state ODE integration. So, but only the solution, and by solution I mean the solution to the ODE at the final time, and that one is t equals capital T. Okay, then we have the third contribution, which is super straightforward. So point 3 is u at capital T contribution from capital T is just the right-hand side of the original ODE evaluated at the final point, which we already have from the primal pass, and the theta vector multiplied with t dot. And then based on these three auxiliary quantities, or these intermediate quantities, we can write down the full push forward rule, and this allows us to forward propagate tangents over the final state ODE integration, or in other words, to forward propagate tangents over an evaluation of our neural ODE. And we have primal inputs, which will be an theta vector, a initial condition, so a u0, as well as a final time. And we also have tangents on those, so we have a theta dot, we have a u0 dot, and we have a capital T dot. And then we will get the push forward operation by first computing the primal, so by evaluating q at theta, u0, and capital T. And then we will push forward our tangents by just adding up all the contributions. So u dot from theta plus u dot from u0 plus u dot from capital T is then the tangent on u at t. So the primal output is u at t, and then the tangent output will be u tangent at t. And here you also see that if in case you only have one or two tangents given, so the other ones are zero, so let's say for instance you only have the tangent on the parameter vector, then of course these contributions will be zero, and this is just an addition, only this contribution will be relevant and you don't have to compute the other ones. And this also shows like how composable these push forward rules are. Okay, let me make an ugly box around here in order to indicate that this is an important finding, and then we see we have found our push forward rule. I want to leave some computational considerations because so far there are quite some details that are left out. So let me call this computational considerations. And the first one is that we can merge the auxiliary ODE problems into one large ODE problems together with the primal pass. Because one point that the additional problems left out is that this Jacobian df by du is not constant. Because in general, if we have a highly nonlinear ODE problem, this will again be potentially also a nonlinear function of u and theta. And as a result, at each point in time where we want to evaluate this Jacobian vector product, either as part of the integration for the tangent contribution from the parameter vector or from the initial condition, we need to also know the primal at that very time. And there are potentially two ways of doing that. We could either first solve the primal and then store the intermediate trajectory and interpolate, or we could integrate it along each other and then we always have access to the primal. And let me write this down in an unnecessarily long sentence. So let's say instead of solving two additional problems, both for r of n degrees of freedom, so this is essentially the size of the vector function we want to integrate, we solve one large r of 3n ODE problem of the tangent propagation. So this is again kept general for both the contributions from the parameter vector as well as the initial condition. And we want to do this together with the primal pass. And as a side motivation, next to maybe reducing the number of calls to our wrapper solver, we also always have the primal values for the Jacobian vector product available. So by this, we also always have the primal values available for the Jacobian vector product. So this is meant with the Jacobian vector product of the right-hand side of the ODE. So these here, the one with respect to u, which appears in both ODEs, and the one with respect to theta, which only appears in the tangent propagation for the theta vector. Okay, so how does that system look like? And let's make that really clear. So in essence, we now have the ODE system, which consists of the primal vector u, then the tangent contribution vector from theta, and the tangent contribution vector from the initial condition. And the dynamics of that system are given that the derivative of the primal will obviously be the function. So it is as before, so this is a primal pass. And then we also have the dynamics for the tangent contribution from theta, which will be the Jacobian of f with respect to u, evaluated at u and theta, multiplied with u theta dot. So I made this more clear here by using this vertical bar in order to indicate evaluation at. And this means we will use the u from the primal pass. So let me make this here. So this will essentially be this u. So at each point, our ODE solver is now querying the right-hand side. He's also able to evaluate the Jacobian vector product. Then plus df by d theta evaluated at u and theta. So again, it's the same u. The theta is fixed throughout the time, so this does not change. So we don't have to worry too much that we always need the most recent version of it. And then we also have the multiplication with theta dot, which is also fixed throughout time. It's given. Okay, then how do the dynamics look for the last component? This will be df by du evaluated at u and theta. Again, same story. This is the u from before, multiplied with u contribution from u0 tangent. And how do the initial conditions look like? So with this same very vectors, so u contribution from theta and u contribution from u0 evaluated at t equals 0 will essentially be the u0, a 0 vector, and the u0 tangent. Okay, and let me again write this down. We had that before, but I just want to also have that in that section of the PDF so that we obtain the JVP, so the Jacobian vector product, which was df by du multiplied with something, or df by d theta multiplied with something, either, so there are two ways, by forward mode autodiff, so we will use any kind of forward mode AD engine that we have available, or we could do that by knowing the Jacobian, and this is especially the case if we have like PDEs or if we have some certain sparsity structure. So for instance, for example, by the sparsity structure of PDEs. And just a remark for neural ODEs that depends a bit on the architecture you're using. So if you use an MLP, then your Jacobian will be dense. But if you use some ConvNet, you can have some sparse Jacobian, but this is really problem dependent. And a really final remark I want to leave here is that the auxiliary tangent linear problems, so these are the additional ODEs we have to solve for the u tangent contribution from theta and the u tangent contribution from u0 will at maximum be as hard as the primal problem since they are always linear. That's a bit tricky to understand. I mean, it is obvious that those are linear systems, so the dynamics of u tangent from theta is given as a matrix times something plus something, so it is a inhomogeneous linear dynamic. But due to the fact that it has this linear structure, it will have less troubles than a nonlinear ODE integration. So for instance, it will also be non-chaotic just because it's not nonlinear. But this does not necessarily mean it has to be like super easy, since the Jacobian here, this matrix, can potentially change really quickly if the original primal problem is also quite tough. So it's really problem dependent, but we can at least say it will not be harder. So this is an interesting insight. So we can propagate tangent information, and later on we will also see that in the reverse mode with the adjoint ODE, in that we can do that at the same cost as a primal evaluation. It might introduce some additional overhead that might have to accept, but in general, it will not cause us like any exponential or polynomial additional cost. And it's an interesting feature of automatic differentiation, or here in that case, you might also call this the tangent linear propagation. Okay, one last summary of the video, because I think it's just such an interesting idea. So we looked at the integration of neural ODEs, or in more general scientific computing terms, it is the final time integration of ordinary differential equations. So you take an ODE that can potentially be nonlinear, it can be chaotic even, and you solve that with your adaptive integrator, so for instance the Runge-Kutta 4-5 integrator. And this problem is parameterized with a parameter vector, an initial condition, and the final time. And now you have tangents on all these inputs and want to propagate them to the output. And you want to do that without unrolling. And then we saw that by the general rule to Jacobian vector products, you have to propagate each of the components individually. And for the first two components, we derived auxiliary ODE problems that have to be solved in order to propagate the tangents. And for the last, it was just a trivial evaluation, but oftentimes the last is not very interesting. And this allowed us to write down the general push-forward rule. Let me recall that here. And then we also made a computational consideration. We could do that by just solving as a larger system of ordinary differential equations, because we need access to the primal solution anyways in order to evaluate the Jacobian vector products in case our system or primal system is highly nonlinear. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. That's the end of the video. It was a tough one. I hope you enjoyed it and you're also ready for the next one, where we will then look at reverse mode automatic differentiation, so the adjoint problem, which was also derived in the neural ODE paper. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There's more awesome content on these automatic differentiation rules. Here you will now see similar videos, and I hope to see you in one of the next videos.